In this video, I want to talk to you about p-values, also called observed significance levels. But in order to do it, I'm going to look back before I look forward. And what I mean by that is I'm going to go back to an example from the last time we got together where we were trying to determine if the average fee of a full-service funeral was less than $7,180. And so you can see the null and the alternative hypothesis we wish to test. The first piece of a test hypothesis is identifying the null and the alternative. We want to test to see if mu is less than $7,180. And by default, we always put the equal to sign in the null hypothesis. So that sets up what it is we're going to test. Knowing the null and the alternative, figuring that out, takes us to the correct menu inside our software to get a printout. And so you can see here, I've actually set that up in the software to where the null and the alternative read like that. And it gives me the test statistic of negative 1.71, and that's a second piece. So the first piece is the null and the alternative. The second piece is get the test statistic. This is the formula part, and I don't want you doing the formulas. We're always going to have printouts available to us. We're always going to have software available to us. So we get a test statistic. Now we need to evaluate it. Well, the way we've talked about evaluating it before is by using what's called a rejection region. And the rejection region says, all right, we're in the lower tail, and this is a terrible picture, sorry, bad start at least. We're in the lower tail of the z-distribution. And so we want to take an alpha, and in this particular case, the alpha that we were using was 0.05. And so I'm going to put 0.05 in the lower region of the z-distribution. And I'm going to need to go to my table and find that. Now, hopefully, let's see if I've done my animations correctly. There we go. Ooh, I didn't realize that my annotations would come over top of it. Anyway, we're going to go to the 0.05 column of the T table. We're going to go all the way down the bottom, and we're going to get this 1.645. And so my rejection region looks like that. Now I'm going to take some of this stuff out because it's going to be in the way. We're going to reject H naught if our test statistic is lower than a negative 1.645. And that's our rule for whether we reject. Now in our case, the test statistic is negative 1.71, which falls further out here in the tail. And so our conclusion that we saw last week was that alpha equal 0.05, we reject. There's going to be sufficient when we reject. There's sufficient evidence to indicate that the average fee is less than 7,180, and this would be the average of all fees, mu, the average of all. And so that's a test we did last week, and so I don't really want to take too much time to go over that because we did see that last week. Now, my question for you that we're going to start with today is, what if I changed alpha to 0.01? Okay, what changes? Does the null and the alternative change? Does this piece here change? Does the first step in the test change? No, not if we change alpha. We're going to do the exact same test. Likewise, the test statistic doesn't change either. This test statistic represents the sample information, and changing alpha doesn't have anything to do with the sample information. So both step 1 and step 2 stay exactly the same. Now, obviously, or maybe not obviously, I'm going to hope it's obvious, if I change the alpha, now my rejection region changes. Think about the picture that I drew over here. Okay, now instead of putting 0.05 in the tail, I'm going to put 0.01 in the tail. So what happens? Well, rather than going down the 0.05 column, we're going to come over here and go down the 0.01 column. Now that critical value, that cutoff point, if you will, changes to 2.326. And so the picture changes. This value, the 1.645 value that we see here, moves out. And notice what happened in this case. It moved out beyond the test statistic. So as I change alpha, now watch what would happen here. If I made alpha bigger, if I made alpha 0.10, can you see how the test statistic would move this direction? So if you're rejecting H naught at 0.05, the negative 1.71, that red line you still see there, that's my test statistic up here. It's further out than a negative 1.645. If alpha was bigger and this line moved this way, well, the test statistic's still going to be further out there. But as my alpha got smaller, as I went to 0.01, we see that that 1.645 number moved to the left, and I should be saying negative. And so the conclusion in this case would change as well. We fail to reject there is insufficient evidence to indicate that the average fee collected in the current year is less than $7,180. When we reject, there's sufficient. When we fail to reject, there's insufficient. And so this is the rejection region approach to making conclusions. You choose an alpha, you go to the table, you find a critical value, you compare your test statistic to it. So at alpha equal 0.05, we rejected, and another way of saying it, 95% confidence, we reject. At alpha equal 0.01 or 99% confidence, we can't reject, we fail to reject. Well, what about 0.02? How about 0.03? How about 0.04? And the point, the bigger picture point that I'm trying to raise here is every time I change alpha, you got to go back to the table. Now, you saw I used the t-table because the values I chose here for my alpha, the 0.01 to 0.05, there were columns in that t-table, and we've seen it before, how we can use that t-table when we go down to the bottom row to get our z-values. But there's table work involved. And that's the piece that I want to try to improve on today. That's the piece that the p-values or observed significant levels are going to help us with, aka also known as p-values. I'm going to tell you three things. First, they tell us how significant our test statistic is. In that last problem, we had a test statistic of negative 1.71. The wording that I'll use, here's how I'll say it. That negative 1.71 was significant at alpha equal 0.05. It was not significant at alpha equal 0.01. So significance refers to our ability to reject H0. We could reject H0 at 0.05. That's why I'll say it was significant. It was further out there than our critical value. It was not significant because we could not reject H0 at alpha equal 0.01. And so the observed significance level tends to quantify how significant our test statistic is. It allows us to easily make conclusions for any choice of alpha. Now, I struggled with the notes here to use that word because easily depends on where your knowledge level is. It's easy for me, but I kind of know this stuff pretty well. Let me say it more easily allows us to make conclusions because my opinion, and you may not agree with me yet, but hopefully you'll get there. My opinion is the rejection region isn't terribly difficult because the rejection region just has us go to the table. Now we got to think through this. Do I use a t-table? Do I use a z-table? Where's my alpha? Which tail do I put it in? So there's some rejection region questions that we have to go through. But it's just it's another answer that we get from the table. Rejection regions always end up in the tables. And so I don't think they're overly difficult, but I'm telling you, the p-values make it even easier. Now there's a little bit of a curve we got to get to. We got to learn some stuff first. But it's going to allow us to more easily make conclusions for any choice of alpha. And the number one reason we like p-values is they're given to us on most computer printouts. And if you flick back to that last page, you can see that the printout has a p-value there. Given to us on most computer printouts. Now you see in parentheses here, with some modifications needed at times. I'll talk about that in a little bit. Okay, that'll come up and through our discussion and through some things we're going to see this semester. The software that we're using this semester is very nice when it comes to p-values. I can ask for a direction of the test and it will give me the p-value for my test. Not all software packages work that well. So these are the three things that are just kind of general ideas, if you will. The three reasons I love p-values. Now, there are the three reasons you love p-values. There are two tasks involved with p-values, and I'm going to say this, and I want you to hear this closely. The first is finding p-values. And typically, we won't need to do this because of what I said right here. They're given to us on most printouts. Now, the reason that I go through and ask you to find p-values, and I'll probably put a question on your exam asking you to do this task, is because once you understand how to find p-values, that's where the understanding of what they're trying to give us comes in. And so we're going to talk about finding p-values, and actually it's going to take us a lot longer to talk about finding p-values than it will the second task, which is interpreting p-values, which, by the way, is the more important task. So just bear with me here. Let me help you with this finding p-values. We're trying to determine, excuse me, how significant our test statistic is. How far out there. If our test statistic in the last problem was a negative 1.71 and we said it was significant at 0.05, imagine if it was a negative 2.71. That's even further out there. That's more significant. Remember, significant refers to our ability to reject H0. It's going to be easier to reject H naught with a negative 2.71 than a negative 1.71. How about a negative 3 or 4 or 5.71? Wow, that would be really significant. That's kind of the idea. So the p-values are trying to quantify, trying to tell us how far out there the test statistic is. And like a lot of things that I give you in class, it's a process. And one of the things I'll say here is the process for finding p-values has some similarities to the rejection region. In fact, it's so much like the rejection region, it's easy to confuse the two. We start with a distribution. When I ask you, how far out there is that negative 1.71, it depends what distribution you're working with. If you're working with a z distribution, that's going to be different than a t distribution with 4 degrees of freedom or 17 degrees of freedom. So we start with the curve, and you can see I have a curve drawn in the upper right-hand corner here. Then we draw in the value to test statistics. So in the purposes, there's the negative 1.71. And now when I ask you how far out there depends upon which direction you're looking. And so here's how I'm going to say it. If you're looking in a greater than test, out there would be to the right. If you're looking at a less than test, out there would be to the left. And if you're doing a not equal to, what's further out there than a negative 1.71 in a not equal to test? Well, both sides. Negative 1.72 is further out there, but so would positive 1.72. And so there's one-sided p-values, and there are two-sided p-values. The p-value is the probability in the shaded tails. Find it using the z-table. So there's the 4 steps. You draw a distribution, you put in your value to test statistic, you shade the direction that you're looking, and that's based on the direction that you're testing in the alternative, and it all goes back to what are you looking at in the alternative? Which direction? Are you looking less than? You're looking greater than? You're looking not equal to? You're looking left? You're looking right? You're looking both tails. And the p-value is the probability in the shaded tails. Now you notice I'm specifying, let me get my cursor down here in the right spot, I'm specifying the z-table. P-values work for t-tables. They work for any distribution that you're working with. However, the tables that we work with, t-tables are a little challenging to work with p-values. So when I ask you, not if, but when I ask you to find p-values, I'm going to make sure you're working with large samples. You're going to be using the z-table. So that's the only examples you're going to see me look at. You're the only ones I'm going to talk about. If I want you to work with p-values with small samples, I'll make sure you have a printout that gives you the p-value, and you'll be doing the interpretations. Okay? So let's take a look at an example. And the example is the one that we've been working through. We want to see if mu is less than 7,180. If I remember correctly, the n in this particular problem was 36. So it was a large sample problem. Okay, large. Why is that a large sample? Because when you're working with means, the sample size is large if n is greater than or equal to 30. If you're working with proportions, it's n times p and n times q both have to be at least 15. There's different sample size criteria. So this is a large sample problem. So we know the test statistic is a negative 1.71. We got that from the printout we saw before. Now let's figure out the p-value. So I'm going to draw you a picture. Okay, I'm going to draw, let's see, large sample. I'm going to draw a normal curve. Whoops. And let's see if I can take that away. Take that away. I can't take that away. I'm going to draw the picture. Shoot. I'm going to draw a normal curve. I'm going to put in the test statistic, negative 1.71. And I'm going to shade to the left. And I'm sorry that the z-table came in too soon. Okay, step 1 is draw the curve. Step 2 is put in the value of the test statistic. Step 3 is shade to the left. And now let's go find the probability. There it is. 0.4564. 1.71, 0.4564. Now it's going to go the other way. 0.4564. That's what the table tells me. So what do I have here? For every test statistic, there are 3 possible p-values. Okay, well, we're doing a less than test. So if we're doing a less than test, the p-value is the shaded region. We would shade to the left. That's the picture that I drew. That's the p-value. Well, if there's 0.4564 in here, what's 0.5 minus that? 0.0436 must be in the tail. That's our p-value. What if we were doing the not equal to test? Okay, this is the picture. This is the less than picture that I've drawn here. What would the not equal to picture look like? Can you see how we draw the curve? We draw in the value of the test statistic. And if we were looking at a not equal to test, which way would we shade? Well, we want to shade both tests. What's further out there than negative 1.71? Well, over here. But wouldn't you also have a positive 1.71 on this side? Let's see if I can draw that a little bit better. And wouldn't you have shaded over here? Can you see how you have a 0.436 on this side? You have an 0.436 on that side. Can you see how it double? The p-value is made up of really both sides. .0872. And so our one-sided p-value and our two-sided p-value, one is half the other, one is double the other, depends how you're looking at it. Why this is important is because sometimes some software programs only give not equal to p-values. So sometimes you look at a printout and you see a p-value like that and you say, wait a second, I want the one-celled test. I have to modify it. That's that note I gave you before. Sometimes you need to modify the p-value that you see on the printout. That p-value is going to be specific to a certain alternative hypothesis. Is it the one you want? Well, if it is, use it. If it's not, modify it. Now there is a third possibility. What if I had a greater than test? What if I had a greater than test? I'm looking to the right, yet my test statistic is a negative 1.71. So I draw the curve, I draw in the value of the test statistic, and then I say shade appropriately. But this case, because I'm doing a greater than test, I would shade to the right. What would the p-value be there? It's not going to be 0.436. That's the shaded region to the left. It's going to be everything else. It's going to be the rest of that probability. So if you have 0.4564 in here, we know on this side we have 0.5. So you add those two things together and you get 0.9564. Notice that these two things, the greater than and the less than p-value, sum to 1. Will they always do that? Yeah. Yeah, they will. The point is, for every test statistic, there are three possible p-values. It depends which test you're doing. It depends everything in a test hypothesis, whether you're working with rejection regions or you're working with p-values. Those are the two ways we're going to have of making conclusions. They all depend on the direction that you're testing. And in this case, we're doing a less than test. So the p-value for the test that we really wanted to conduct is that first one you see there, the 0.436. That's the process. Draw the distribution, draw in the value of the test statistic, take a look at the alternative and shade the correct way, and then you go to your table and you find the probability involved. That's the finding the p-value. How about interpreting? Well, interpreting the p-value, really easy. If p is low, reject the null hypothesis. If p is high, we fail to reject. It's that simple. And you're going to know there's a couple different ways of remembering this. For years and years and years, I talk about alpha and the p-value. And when I first started teaching, someone asked me about the fish. I was like, what are they talking about, the fish? And they were referring to alpha because the Greek letter alpha, of course, looks like a fish. And especially if you draw it more elongated, right? There's my fish. And so they said, I'm having trouble with the fish. And I was like, gosh, I don't understand. And then they showed me alpha. And I was like, okay, that makes sense to me. And so I started using that and saying, well, fish, if I let that represent the fish, I used to own a house that had a pond. Imagine if I got up and I looked outside and there was this fish that was bigger than the pond. And so if p is small, or if alpha is big, if the fish is bigger than the pond, if alpha is bigger than the p-value, you reject. And so that was the example that or that's the way I help students remember it. If the fish is bigger than the pond, something must be wrong. Right? A fish bigger than the pond, that doesn't make any sense. We reject H naught. And I used that for years and years and years. And I think I used it fairly effectively. Probably about 5 years ago, I was teaching a class, and there was a student in the class who they listened to that and they were very polite. And then she said, I got a better way. and always wanted to look for other ways. And actually, I was a little skeptical if I would want to be quite honest. I said, really? You have a better way than the fish in the pond? I thought that was outstanding. She said, yeah, my teacher in AP Stats had a better way of remembering it. And I said, all right, what do you got? And she said, when P is low, reject the hoe. And I said, no, that's not going to work. When P is low, reject the hoe. And so I had a little competition in that class and in my other classes. And I was wrong. That's an easier way of remembering it. So when P is low, we reject the null hypothesis. When P is high, I would love to say, I've been trying to come up actually with another saying. When P is high, let it fly. It doesn't make any sense. It doesn't work. When P is low, reject the hoe. When P is high, we fail to reject the hoe. That's it. It's simple. When P is low, reject the hoe. This works for every test hypothesis you're ever going to run into. It's a beautiful little way of remembering how to interpret p-values. So in our example, the p-value is 0.0436. If we're testing at alpha equal 0.05, is p-value low? It is. We reject HO. When we tested alpha equal 0.01, is p-value low? Well, it isn't, right? 0.04 isn't lower than 0.01. We fail to reject. It really is that simple. Remember how I talked about earlier, if I say, what if alpha is 0.02? The rejection region says, hold on, let me go and run to the table. Let me find my critical value in the table, and let's compare our test statistic to it. Again, I don't think that's an overly difficult way of making a conclusion. You got to go and use the z-table again. Ooh, z-table. How many times have we done that this semester, right? However, the p-value method's easier. If I'm comparing it to an alpha equal 0.02, is p low? No. P's high. We'd fail to reject. At 0.03, we'd fail to reject. At 0.04, we fail to reject. At 0.044, we'd reject. At 0.01, fail to reject. At 0.10, we reject. We compare this number to the alpha we're testing at. If that's lower, if the p-value is lower, we can reject H naught. It's summarized right there. When p is low, reject the hoe. This works in large sample cases. This works in small sample cases. This works for means. It works for proportions. When we compare means, when we compare proportions, when we do regression analysis, when we do any kind of test hypothesis, categorical data analysis, analysis of variance, all sorts of words and tests and things I'll throw at you that you'll see in this class and then beyond, they can all be interpreted the same way. And so if you take a look at this video that I've made and you look at how much time I devoted to finding p-values, it was a big chunk of time. You're not going to do a lot of that. That helps you understand what they're trying to do. P-values are they're attempting to quantify how far out there our test statistic is. I'm going to ask you to find one p-value for me probably. More often than not, I'm going to give you a printout and I'm going to ask you to interpret the p-values. You do need to be careful. Make sure the printout has the p-value for the test you're conducting. For instance, if the p-value has a less than test that's being conducted, but you really want to do a not equal to, it's going to give you a less than p-value. If you're doing a less than test, go ahead and use it. If you're doing a not equal to, you got to double that number. So the computer's going to do a lot of the work for you, but you got to be a little aware. Is that the p-value I want? Once you say, yes, that's the p-value I want, now just ask, is it low? If this is the test we were conducting and we were using a 0.05, that's a fail to reject because p is high. And so there's some thought that goes into it. Now we'll take a look at some examples and I'll show you how to do that. But that's our p-value discussion. So I'm going to end this video here and we'll come back and we'll take a look at some examples and we'll probably do some small sample work too. I'll probably combine those into one. So long.